All right. GPU clusters. Everyone here understands about GPU shaping.
You're lucky the process guys on here today.
Yeah. So yes, question.
Sorry for the ignorance, but why is it that GPUs can't really communicate that easily?
It's to do with this communication, the software. It's not that they can't. It's that the software paradigms have not caught up yet to allowing people to write applications. Because you must remember, GPU applications are actually very problem specific. Until there's a need to scale that, they're not going to put in effort to do that. So it's only now getting to that point where people are saying we need to scale our problems and GPUs are the best for it. How do we do that across nodes? So that's where this comes in. It takes MPI, you can see the MPI part there. The MPI-CH is a open source implementation, and this part looks at the GPU side of things. Okay.
It's not the architecture.
It's not the architecture. It's literally the network communication and how the software knows to communicate where.
So typically you wouldn't be doing something on a GPU at the same time you'd be doing something on a CPU. So why does each GPU belong to a node which contains CPUs? Could it be a separate node?
You can actually do CPU and GPU simulations. So there's a cross-couple simulation. ANSYS do this quite well with a discrete element modeling that uses the GPU only. Then they've got fluid. So there's fluid flow as well as rocks. I want to simulate all of this. So it's a cross-coupled. So the fluid flow uses all the CPUs and RAM, and the discrete element modeling uses all of the other stuff.
To each other.
And they do talk to each other. Yeah. So and how they talk to each other is through your data. Okay. Any other questions? Yes.
Maybe you'll talk about this data at a high level, but just the kinds of problems that you would solve on GPU clusters versus CPU clusters, and then also FPGA clusters.
Okay.
But I don't know if maybe you can talk about it.
I wasn't going to go to FPGAs, but we can go into FPGAs. Let's first talk about CPU, GPU, and then we'll go to FPGAs. So CPUs are general processing. The architecture is to be able to do general stuff, all sort of stuff, which means they sacrifice optimizing certain things. But matrix inversion, all of those things. Now this might show my age. Does anyone remember a map coprocessor? You might.
I'm still done getting it.
So does everyone remember a Pentium?
Yes.
Yes.
A 486?
Yes.
Yes.
A 386?
Yes.
I think I used one once.
You used one once, right. The early versions of a 386, the CPU couldn't do floating point operations well. And there was actually a separate slot in the motherboard called the math coprocessor. You plugged it in. Over time, they merged together because it was just natural. And a similar thing is happening with GPUs. You'll notice that Intel has got a GPU on chip. So they're starting to merge. That doesn't go to answer your question. So the question is, general problems, matrix inversions, those codes are all written really well for CPUs. GPUs are only good at specific problems. They're not general purpose sort of problems. And at certain applications like computational chemistry, and only certain parts of it are good on GPUs. So it depends on the code and if the code allows it, what they do. FPGAs. Does everyone know what FPGA is? There's a no there, not necessarily.
Well,
So,
I said not necessarily, but everyone knows what an FPGA is. Students, how many of
Good
you
catch,
know what an
Danny, good catch.
FPGA is? So any of our graduate students know FPGAs?
does anyone know what it stands for?
I know. Field Programmable Data Array.
Yay! Okay. So what does it actually do?
Lots of logic.
It's good. Like the name says, it's a programmable thing. You can actually program an algorithm into it, and it's really good at that one algorithm. But programming it is not trivial, and changing it and asking it to do other things is also not that good. So it's very good for specific things. Bitcoin, you don't know what Bitcoin is, yes? So that algorithm that they're trying to optimize as much as possible, so they use, or used to use FPGAs to put that algorithm on, and so everything else becomes terrible. And they've taken it a step further. Everyone know what ASICs are? What does it stand for?
Application-specific integrated circuits.
There we go. Application-specific integrated circuits. So they take FPGAs a step further and they actually create a chip that does only that one algorithm. So you can almost take that as a line. ASICs, very good, one thing only. FPGA is very good, one thing only, but it can be programmed to do different things. It's quite missions. GPUs, much more general, but only in certain areas. CPUs, pretty much everything. But the efficiency sort of goes up and down as well. Does that answer your question?
Yeah, because I think one of the reasons that FPGAs were designed was so that the obsolescence rates of CPUs, but particularly GPUs, is really high. So 2 years, for example, a GPU, and it's heavily outdated, and then the FPGA was more reusable, and then sort of stay valuable for longer. I don't know if that's...
So what they use FPGAs for in chip design is simulating that it actually works. So they use FPGAs when you get a new Pentium or a new whatever it is. All the design is actually done on FPGAs, and every clock cycle they need to simulate every state, and they use FPGAs for those sort of things. Cool. Any other questions? One there. Okay, so that's GPU cluster.